BC Calculus, lesson 4.1, the chain rule. So this is going to start out really not super challenging, but some of the problems are very time consuming, and you'll see why. There's just lots of steps. So we call this a composite function because we have the function x squared minus 4 buried inside the function sine. So we want to find dy dx. Well, we're going to break that into y equals sine of u. So we'll take dy du, and then we take du dx. As you can see, those would cancel out. We just left with dy dx. So this is how we do it. Dy du is just derivative of sine is cosine, and du dx is 2x. And we're done. So that looks straightforward enough, but trust me, it gets a little nasty. That's called substitution, and it's a concept used a lot in calculus, where you just make things simpler by subbing something out to get rid of it, and then you can work on something easily, and then you bring it back in later. Some people say, I don't use substitution, I just do outside in. So this is the outside, the 2. So if we find y prime, it's just 2 times 3x squared plus 1. Right, so just power rule like we were doing the derivative of x squared. But then we have to do the derivative of the inside. And this is how I typically do them. Times 6x. And then we do a tiny bit of algebra. Sometimes we do a lot of algebra, especially with trig problems. Sometimes we just leave them. Sometimes we rationalize them. Sometimes we don't. Again, that's the big hassle, not the calculus per se, but there's a lot going on, and it's hard to keep it all perfectly consistent. But that's the outside-in method. Do the outside first and the inside second. So that example just showed you why it has to work, and this is what I did above. And this is the composite as written, and all this fun stuff. So here's an example. Object moves along the x-axis, so its position at any time t greater than 0 is given by this formula. Find the velocity. So velocity is first derivative. So we have the cosine of a function, so the derivative of cosine is negative sine, and the function does not change on the inside. And then we do the derivative of the inside, and we end up combining it so it looks nice. So again, outside and then inside. Really doesn't look that bad until you end up doing derivatives like 3 or 4 times. So differentiate. I really should have something in there, but let's be lazy. d dx of sine of x squared plus x equals cosine of x squared plus x times 2x plus 1. So the outside and then the inside. And I'll put the 2x plus 1 out front. No, I won't distribute it. Would it be wrong if you distributed it? No, of course not. So, like I said, hey, no problem, I'm good at this. Yeah, now we're going to have to do it again and again and again and again. Differentiate. G prime of t equals secant squared 5 minus sine of 2t times the derivative of the inside, which is negative cosine of 2t times the derivative of the inside of that, which is 2. Negative 2 does not matter what order I put this in. I'm going to keep the cosine of 2t out front. And this is what I mean by complexity. Not, well, I really didn't know what happened there. Yeah, there's a lot of little calculus, but then if you had to combine that or if you had to plug values in, it gets very challenging. We're going to bring parameterized curves back in. Been working on pronouncing that. I'm pretty proud of myself. And notice that dy dt is dy dx times dx dt. You can actually, like we just did, the inside outside, you can actually set it up so that you look at dy dx as just dy dt over dx dt. So if somebody says, here's a parametrically defined function, and you want to find dy dx, well, you need to find dy dt and divide by dx dt. As you can look at that, the dt's cancel out, and you're left with dy dx. So y equals tangent secant squared t. Derivative of secant is secant t times tan of t. And we get a little bit of math here. Secant t, and I'm going to put tangent up top as cotangent t, and we might be able to cancel 1 over cosine, cosine over sine. We are able to cancel 1 over cosine times cosine over sine equals cosecant of t. And they say, do me a favor, find the line tangent to the right-hand hyperbola defined by this thing. It's at the point, and t equals pi over 4. So what's the slope? Cosecant of pi over 4, which is 1 over root 2 over 2, which is just root 2. And then something I'm starting to do this unit is write it in both point slope. X minus root 2 plus 1, and then in slope intercept, which I recommend just getting good at it. Minus 2 plus 1 equals root 2x minus 1. Either answer is acceptable. So I'm buzzing through a boatload of math here. Slow it down and pause it and redo it if you have to. Graph the info from above and see if it makes sense. So we need our handy dandy calculator. And we're going to go and shrink this down to size so that it's going to fit on the screen. That should do it. No, it's not bad. Mode, parametric, y equals x is secant of t, 1 divided by cosine of t, and then y is tangent of t. Tangent of t. Make sure we're in radians. We are. Let's go ahead and graph that. So I guess that my t-value is a little off. I'm going to go from -1 to 1. That seems to help. I want to zoom in a little bit. I want to go from -5 to 5, and from -5 to 5. Let's see if that makes it better. This takes its time. Eventually does the other side. Not in this case. Looks like it's done. So let's try one more time and make it go from 0 to 10. Let's see what happens. That basically shows the asymptotes. It does it all twice. That's fine. The equation we just got was Root 2x minus 1. So I have no idea because I don't have a scale on here. Root 2x is up 1.4 and over. So something like that. And that's supposed to hit the point. Root 2 comma 1. So out here, root 2 comma 1. So looks like it's tangent. Hard to tell. Good to graph in practice. So let's see if you can do this one. You can pause the recording and try it yourself. Find the slope of the line y equals secant to the fifth x at the point where x equals pi over 3. So pause if you want because I'm just going to run and do this. Y prime equals 5 secant of x time to the fourth. Let's put the right spot, to the fourth times secant x tangent x, which is equal to 5 secant to the fifth x times tangent of x. We're just finding the slope of the line. So we plug in x, 5 times secant to the fifth pi over 3, tangent of pi over 3. Cosine of pi over 3 is 1/2, so we have 5 1/2 to the fifth. And tangent of pi over 3 is root 3. So we should, checking my work here, making sure I'm happy with what I see. Yep, we should get 5 root 3 over 32. Tricky. Yeah, tricky stuff. So this is called using the power chain rule, but I'm sure you already figured that out. You just have some value to the fifth, and you put that out front, and then you take the derivative of that value with respect to x. So in this case, it was secant to the fifth. Just to give you more practice, let's see if that was sine to the fifth, where x equals pi over 3. What is the slope? 5 sine of x times cosine of x. Y prime equals 5 times sine of pi over 3, root 3 over 2. And that's to the fourth, so I just realized I made a mistake on that previous one. This should be to the fourth. I just didn't carry it through right. So this should be to 16 times cosine of pi over 3, which is 1/2. So I end up with 3 times 3 is 9, times 5 is 45 over 32. Very cool. That's it. Get to work. And as always, happy mathing.